Hey there, curious minds. Have you ever looked at something as common as the aluminum in your laptop, or maybe the copper in a wire, and really stopped to wonder what's happening inside it, down at the atomic level?
Uh-huh.
Today, we're taking you on a deep dive into that hidden world. We're aiming to give you a shortcut, really, to understanding the invisible architecture of solid materials.
That's the plan.
Our mission is to unpack a core chapter from Materials Science and Engineering by Callister and Rethwish, but importantly, in a way that makes these complex ideas crystal clear without needing a single visual.
Exactly. Think of it as uncovering the secret language of atoms. Understanding why, say, a diamond is incredibly hard, or why glass is clear, or how metal can bend.
It sounds fundamental.
It really is. The seemingly simple act of atoms forming a solid actually conceals this incredibly rich and intricate architecture. We're going to explore this step by step.
From the basics.
Yeah, from the most fundamental distinctions between materials all the way to how we can actually see these atomic patterns using some pretty clever techniques.
Okay, I'm ready. Let's unlock this. So, to start, what's the most basic way we categorize solids when we think about their internal structure? Are they just, random piles of atoms?
Not at all. That's actually the very first distinction we make. We classify solid materials into two main categories based on how their atoms or ions are arranged inside.
Okay.
First, there are crystalline materials. These have what we call a long-range order. Imagine atoms positioning themselves in a perfectly repeating periodic three-dimensional pattern. And this pattern extends over vast atomic distances.
Like really regular.
Yeah, think of it like a perfectly stacked brick wall where every single brick is in its designated place, repeating a precise design over and over. Most metals, many ceramics, and even some polymers fall into this category.
Okay, the perfect brick wall. What's the alternative then?
The alternative is non-crystalline, or sometimes we call them amorphous materials. These materials lack that long-range atomic order. Their atoms are arranged more randomly.
More like a jumbled pile?
Kind of, yeah. Much like they would be in a liquid state, but they're frozen in place. The term amorphous literally means without form, and sometimes you'll hear them called supercooled liquids.
So, okay, a perfectly ordered wall versus a more chaotic pile. I can already sense this order or lack of it must directly affect a material's properties, right?
Absolutely. That's where it gets really
Can you
interesting.
give some examples?
Sure. Take pure magnesium or beryllium. They are crystalline, very ordered, and they tend to be quite brittle. Now, compare that to gold or silver. They also have a crystalline structure, but it's a different type of structure, and they're much more malleable, much easier to shape.
Huh. Same state, different properties just from the arrangement.
Exactly. Or consider this. Non-crystalline ceramics and polymers are typically transparent. Think of a clear glass window that's amorphous silica, but take the same material, silicon dioxide, in a crystalline form, like quartz or a frosted ceramic tile, and it tends to be opaque or translucent.
Wow, so transparency can literally come down to whether the atoms are lined up neatly or not.
Often, yes. That underlying atomic order plays a huge role.
That's a huge difference. But how do we even begin to describe these microscopic atomic arrangements? We can't just look. Do we have a way to model them?
We do. We use a simplified model called the atomic hard sphere model. Basically, you picture atoms or ions as solid, perfectly round spheres with defined diameters.
Like tiny billiard balls.
Kind of, yeah. And in this model, nearest neighbor atoms actually touch one another. This lets us map out their positions in space relative to each other.
Okay.
Now, if you imagine a three-dimensional array of points that coincide with the centers of these atomic spheres, we call that a lattice. It's like the underlying grid or framework.
And the smallest repeating section of that lattice, the basic building block, I think I've heard that called a unit cell.
That's it exactly. A unit cell is the smallest repeating entity. If you take this unit cell and copy it, then shift it along its edges over and over, you can generate the entire crystal structure.
So it's like the single Lego brick that makes up the whole castle.
That's a great analogy. For most structures, you can picture it as a sort of building block, often a parallel piped, like a cube or maybe a slightly squashed box shape. It's chosen carefully because it represents the fundamental symmetry of the crystal structure, and it defines everything about it, the geometry, the size, and the precise positions of the atoms within it.
So what do these basic building blocks look like for the metals we encounter most often? You said most metals are crystalline.
Right, and most common metals exhibit one of three relatively simple crystal structures. This is largely because metallic bonding is generally non-directional,
Clean.
meaning the atoms aren't fussy about bonding in specific directions, they just want to pack together as tightly as possible to minimize energy. This leads to very dense packing arrangements.
Okay, let's dive into these big three structures then.
Okay, first up is face-centered cubic, or FCC.
FCC, got it.
So imagine a perfect cube. Atoms sit at each of the 8 corners of this cube. And then you have an additional atom placed right in the center of each of its 6 faces.
Okay, corners and faces. Like if you glued an extra atom onto the middle of each side of a die.
Exactly like that. And if you were visualizing them as hard spheres, the atoms would actually touch each other along the diagonal line across each face. Some really common examples you'd know are copper, aluminum, silver, and gold. They all have this FCC structure.
And how many atoms are effectively inside one of these FCC unit cells? Because the corner and face atoms are shared, right?
Yeah, they're shared. When you account for the sharing, each corner atom is shared by 8 cells, each face atom by 2. It works out that each FCC unit cell effectively contains 4 atoms.
4 atoms per cube. And how efficiently do these atoms pack together in FCC?
Very efficiently. Each atom in an FCC structure is directly surrounded by 12 nearest neighbors. We call that its coordination number, 12. And the fraction of the unit cell volume that's actually occupied by atoms, assuming they're hard spheres, is called the atomic packing factor, or APF.
And for FCC?
For FCC, the APF is Barger's 0.74. This is actually the maximum possible packing density you can achieve with spheres of the same size. So it's an incredibly dense and efficient arrangement.
Ah, and you mentioned that high packing might relate to why metals like gold are ductile.
Precisely. Those closely packed planes of atoms can slide past each other more easily, which allows the material to deform without fracturing.
Fascinating. Okay, that's FCC. What's the next common structure?
Next, we have body-centered cubic, or BCC.
ECC, okay.
This is also a cubic unit cell. Like FCC, atoms are located at all 8 corners, but instead of atoms on the faces, there's a single atom positioned right in the very center of the cube itself.
So corners and one right in the middle.
Yep. That center atom touches all 8 corner atoms, connecting across the cube's main body diagonals. Think of chromium, iron at room temperature, tungsten. These are typical BCC metals.
Yeah, and the number of atoms per cell for BCC.
For BCC, you have a 1 atom fully inside, plus the 8 corner atoms, which collectively contribute 1 more, since 8 corners, 18 per corner ASOV. So BCC has 2 atoms per unit cell.
2 atoms. And its coordination number, is it still 12?
Nope. For BCC, the coordination number is 8. Each atom has only 8 nearest neighbors.
Ah, so fewer neighbors than FCC. Does that mean it's less densely packed?
Exactly. The atomic packing factor for BCC is 0.68. It's slightly less densely packed than FCC, which makes sense given the lower coordination number. And this seemingly small difference in packing can have a noticeable impact on properties.
Right. Okay, FCC and BCC, both cubic. What's a third type? I know not all metals sit into a perfect cube.
You're right. That brings us to the hexagonal close-packed, or HCP structure. This unit cell isn't cubic, it has a hexagonal prism shape.
Hexagonal. Okay.
Imagine a hexagon on the top face and another identical one on the bottom face. You have atoms at each of the 6 vertices of these hexagons, and also 1 atom right in the center of each hexagonal face.
Top and bottom hexagons.
Right. Then, nestled between these 2 hexagonal planes, there's another layer of plane with 3 additional atoms. These 3 atoms fit perfectly into the triangular depressions formed by the atoms in the layers above and below.
Okay, that's harder to picture just from words, but I get the layered idea. Examples.
Common HCP metals include cadmium, magnesium, titanium, and zinc.
And the atoms per unit cell for this hexagonal structure.
It's a bit different to calculate because of the geometry involving corner, face, and interior atoms, but it comes out to 6 atoms per unit cell for HCP.
6 atoms, okay.
Yeah.
And how does its packing compare to FCC and BCC? What's its coordination number and APF?
Interestingly, the coordination number for HCP is 12, just like FCC.
Oh, really? Same as FCC?
Yep, and its atomic packing factor is also 0.74 again, the same as FCC.
Wow. So different shapes, different stacking, but the same maximum packing efficiency.
Exactly, that's a critical takeaway. Both FCC and HCP are considered close-packed structures. They achieve the maximum possible packing density for spheres of the same diameter, just through different stacking arrangements.
Okay, so we have these precise atomic blueprints, FCC, BCC, HCP. What's one of the first things engineers or scientists can actually do with this knowledge?
Well, a very practical application is computing the theoretical density of a metal. If you know the crystal structure, say FCC, you know it has 4 atoms per unit cell. You know the atomic weight of the element from the periodic table, and you can calculate the volume of that cubic unit cell if you know the atomic radius.
Which you can often find from experiments.
Right. With those pieces, number of atoms per cell, N, atomic weight, A, unit cell volume, VC, and Avogadro's number, Na, you can calculate the density using the formula rho VCNA, VCNA.
And does it match reality?
Remarkably well, usually. For example, if we calculate the theoretical density for FCC copper using its known atomic radius and weight, the calculated value is extremely close to the density you'd measure in a lab. It's about 8.89 gcmol calculated versus 8.94 measured.
That's impressive agreement. It really shows this atomic model works.
It does. It highlights the predictive power of understanding these crystal structures.
So knowing the structure lets us predict density. But what if a material isn't content with just one crystal structure? Does that ever happen? Can they change?
It absolutely does, and it's a really important phenomenon called polymorphism. This is when a material can exist in more than one crystal structure. The structure it adopts usually depends on external conditions like temperature and pressure.
Polymorphism.
And when this happens in a pure elemental solid, like iron or carbon, we give it a special name: allotropy.
Ah, allotropy, like carbon.
Carbon is the classic example. Graphite is the stable form, the allotrope you find at ambient conditions. But under extreme pressure, carbon atoms rearrange into the diamond structure, a completely different allotrope with vastly different properties, obviously.
Right, graphite is soft, diamond is hard. That's a dramatic change from just rearranging atoms. Any other examples?
Pure iron is another great one. At room temperature, pure iron is BCC. But if you heat it up past 912 degrees Celsius, it transforms into an FCC structure. Then if you heat it even higher, it changes back to a BCC structure before melting.
Whoa, it switches back and forth.
Yeah. And these transformations are really significant because they usually come with changes in density and other critical properties, like how easily it can be shaped. Engineers designing things with steel, which is mostly iron, have to know about and account for these transformations.
Makes sense.
There's even a fascinating, kind of infamous historical anecdote related to this. It's sometimes called the tin disease or tin pest.
Tin disease, what's that?
Well, common white tin, the silvery metal we know, has a particular crystal structure called body-centered tetragonal. But below about 13.2 degrees Celsius, so fairly cold, it can slowly transform into a different allotrope called gray tin, which has a diamond cubic structure, like diamond or silicon.
Right, so it changes structure when it gets cold.
Yes, and here's the kicker. This transformation causes a huge volume increase, about 27%, and a significant decrease in density. The gray tin is brittle and just crumbles into powder.
No way.
Normally, this transformation is incredibly slow. But in very cold conditions, like the harsh Russian winter of 1850, it apparently accelerated dramatically. There are stories of tin buttons on soldiers' uniforms literally crumbling away, and even church organ pipes made of tin disintegrating into dust.
That's incredible, just from a change in atomic arrangement due to the cold.
It really highlights how temperature can fundamentally alter a material's structure and, consequently, its physical integrity.
So the very structure can shift. Given all this diversity, FCC, BCC, HCP, polymorphism, how do scientists even categorize the vast number of possible crystal structures out there? Is there a system?
There is. We group them into crystal systems, and this classification is based purely on the geometry of the unit cell. We don't worry about where the atoms are inside the cell for this classification, just the shape of the box itself.
Just the shape.
Yeah, specifically the lengths of the unit cell edges, we usually call them A, B, and C, and the angles between those edges, alpha, beta, and gamma. Imagine a standard XYZ coordinate system. These edge lengths and angles define the shape of that fundamental building block.
Okay, how many systems are there?
There are 7 crystal systems in total: cubic, tetragonal, hexagonal, orthorhombic, rhombohedral, which is sometimes called trigonal, monoclinic, and triclinic.
7 basic shapes.
Right. The cubic system, as the name suggests, has the highest symmetry. Think of a perfect cube. A equals B equals C, and all angles are 90 degrees. FCC and BCC structures fall into this cubic system.
Makes sense.
And at the other end, the triclinic system has the lowest symmetry. None of the edge lengths are necessarily equal, and none of the angles are necessarily 90 degrees. It's the most general, least symmetrical shape. The HCP structure we talked about falls within the hexagonal system.
Okay, so 7 systems based on the unit cell's geometry. Now, we know the overall structure, But how do we talk about specific locations within that structure? Or specific lines or surfaces? Like, if I'm an engineer and I want to describe exactly where a crack started or which plane atoms are sliding on.
That's a crucial point, especially when discussing defects or deformation. We need a precise language and addressing scheme. We use crystallographic point coordinates, directions, and planes. Think of it as a crystal's internal GPS system.
GPS for atoms, I like it. How do point coordinates work?
For point coordinates, we specify a location within a single unit cell using three numbers, often written as QRS. These numbers are fractional multiples of the unit cell's edge lengths, ABC, along the X, Y, and Z axis.
Fractional multiples.
Yeah. So the origin corner is usually 0, 0, 0. The opposite corner might be Hanon 1.
Right.
A point exactly in the center of the unit cell would be 12, 12, 12. A point in the center of the face defined by the X and Y axis would be 12, 12, 0. It gives us a precise address relative to the unit cell edges.
Okay, that makes sense for pinpointing locations. What about specific pathways or lines through the crystal?
For that, we use crystallographic directions. These represent a line or a vector within the crystal lattice. We determine these by basically finding the coordinates of the vector start and end points within the unit cell, subtracting them, normalizing by the unit cell dimensions, and then simplifying to the smallest set of integers.
Integers.
Right. We enclose these integers in square brackets, like of W. For example, the direction 100 represents a vector pointing purely along the positive x-axis from the origin 0, 0, 0, 0, 0, 0 to the point 100. The direction 110 would go diagonally across the bottom face of the cube from 1000, 0, 0 to 111, and 111 cuts through the body of the cube from corner 0, 0 to the opposite corner 111.
So the numbers tell you how many unit lengths it travels along each axis.
Essentially, yes, after simplification. And a bar over a number, like 1 and dia, indicates a negative direction along that axis. These directions are vital because things like stiffness or how easily atoms move can be very different along 100 versus a 1 or 11, for instance.
Because the atomic spacing is different along those lines.
Exactly. And sometimes directions that are crystallographically equivalent, meaning they look the same from an atomic perspective, with the same spacing, are grouped into a family denoted by angle brackets like 100. In a cubic crystal, 100, 0, 10, 0, 0, and their negatives are all equivalent, so they belong to the 100 family.
Got it. Points, directions. What about flat surfaces or slices through the crystal?
Those are crystallographic planes, and we represent them using a different notation called Miller indices. These are enclosed in parentheses like HKL.
Parentheses for planes, brackets for directions.
Correct. Determining Miller indices is a bit different. First, you find where the plane intercepts the X, Y, and Z axes in terms of the unit cell dimensions, ABC. Let's say it intercepts at ABC. If it's parallel to an axis, the intercept is considered infinite.
Okay, find the intercepts.
Then you take the reciprocals of these intercepts, 1a, 1b, 1c. Then you normalize these reciprocals by the lattice parameters, a, b, c, though often it simplifies nicely. Finally, you reduce these fractions to the smallest set of integers, h, k, and l. Those integers are the Miller indices, HKL.
Reciprocals and then smallest integers. Seems a bit abstract. Can you give examples?
Sure. Think of the top face of a cubic unit cell. It intercepts the z-axis at 1, say, but it's parallel to the x and y axis, so those intercepts are infinity. The reciprocals are 1 xi, 1 hane, that's 0, 0, 1. So the top face is the 0, 0, 1 plane.
Oh, okay.
What about a plane that slices diagonally, cutting the x-axis at 1a and the y-axis at 1b, but is parallel to the z-axis? Intercepts are 1, 1 xio, reciprocals are 11, 11, 1 xia, which gives 1, 1, 10. That's the 110 plane.
Got it. And what about one that cuts all three axes, say at 1A, 1B, and 1C?
Intercepts 1, 1, 1, reciprocals 1, 1, 1, that's the 111 plane. These planes are incredibly important for understanding things like surface reactions, crystal growth, and especially deformation. Well, as we'll see, the way atoms are arranged on a specific plane, like a 110 plane, looks different in an FCC crystal compared to a BCC crystal, even though they're both called 110. And that arrangement affects properties.
Right. And is there a special relationship between directions and planes in cubic crystals?
Yes, a very handy one. In cubic crystals only, a direction HHL is always perpendicular to the plane HLL that has the same indices. So the 100 direction is perpendicular to the 100 plane. That's not generally true for other crystal systems, but it's a useful shortcut for cubic materials.
Okay, so these indices give us a really precise way to map everything inside the crystal. Points, lines, surfaces. That seems incredibly powerful for predicting how a material might behave.
It is, and we can take it even further by calculating things like linear density and planar density.
Density along a line and on a plane. What does that tell us?
Linear density, LD, measures how many atoms are centered along a specific direction vector per unit length of that vector. Think of it as how tightly atoms are packed along a certain path. Planar density, PD, measures how many atoms are centered on a particular crystallographic plane per unit area of that plane. It tells you how densely packed a given surface is.
And why do we care about how tightly packed atoms are on lines and planes?
This is absolutely crucial for understanding deformation, especially in metals. It relates back to that idea of slip.
Slip, like atoms sliding past each other.
Exactly. Slip is the primary mechanism by which metals plastically deform how they bend or change shape permanently without breaking. And here's the key. Slip occurs most easily on the most densely packed crystallographic planes, those with the highest planar density. And within those planes, it occurs along the directions with the highest linear density.
Ah, so the densest planes and the densest directions on those planes are the easy glide paths for atoms, like a deck of cards sliding easily on the flat faces.
That's a perfect analogy. The atoms prefer to slide along these densely packed pathways because it requires breaking and reforming fewer bonds, less energy is needed.
So those highly efficient FCC and HCP structures we talked about earlier, the ones with the maximum APF of 0.74,
Yeah.
they must have some very densely packed planes, right?
Absolutely. That's why they're called close packed structures. Their high overall packing factor comes from having these specific, very dense planes.
And how do these close packed structures actually form? Is there a specific way these dense planes stack up?
Yes, there's a very specific way they stack. You can think of both FCC and HCP structures as being built by stacking layers of these close-packed planes of atoms on top of each other.
Stacking layers.
Yeah. Imagine a single layer, a flat plane where each atom is surrounded by 6 others in a perfect hexagonal arrangement. Now, look at the little triangular depressions or hollows between groups of 3 adjacent atoms in that first layer. Let's call the positions of atoms in this first layer A sites.
Okay, A sites.
When you place the second layer of atoms, they will nestle into one set of these depressions. Let's call these B sites. So now you have an A layer and a B layer.
A and the B.
Now for the third layer, there's a choice. If the third layer's atoms are placed directly above the first layer's A sites, the stacking sequence becomes AB-gab. This stacking sequence generates the HCP structure. The close-packed planes in HCP are typically the 0001 basal planes.
Okay, ABAB gives you HCP. What's the other choice for the third layer?
The other choice is to place the third layer's atoms in the other set of depressions, the ones that weren't used by the B layer. Let's call these C sites. So the stacking sequence becomes ABCA, BC, ABC. This sequence, where the third layer is offset from both A and B, generates the FCC structure.
ABC, ABC. Gives FCC. Interesting.
Yeah. And in the FCC structure, these close-packed stacking planes actually correspond to the family of planes we talked about earlier, those planes that cut diagonally across the cube corners.
So the same highest packing density, but achieved through 2 distinct stacking patterns, leading to 2 different overall crystal structures, HCP and FCC.
You've got it.
We've spent a lot of time on these perfect, ideal atomic arrangements. But what about the actual materials we encounter every day? Are they all perfect single crystals like this?
Not usually, no. It's really important to distinguish between 2 types of crystalline solids. First, you have single crystals. These are materials where that periodic, repeating atomic arrangement is perfect or very nearly perfect and extends continuously throughout the entire piece of material without any interruptions.
Like a perfect, unbroken brick wall.
Exactly. These can be grown artificially under controlled conditions, and they are absolutely critical for many modern technologies. Think about the silicon wafers used to make computer chips. They need to be incredibly perfect single crystals for the electronics to work reliably. Sometimes naturally occurring crystals also have very regular geometric shapes reflecting this internal order.
Okay, so single crystals are rare and often engineered. What's more common?
Much more common are polycrystalline materials. The vast majority of crystalline solids we encounter metals, ceramics, are polycrystalline. This means they're actually composed of many small individual crystals, which we call grains.
Many small crystals stuck together. How do they form?
Imagine a liquid metal cooling down and starting to solidify. At various points within the liquid, tiny nuclei, which are just miniature crystals, start to form. Critically, these nuclei usually have random orientations relative to each other.
Okay, random little starting crystals.
Then these tiny crystals grow outwards, consuming the liquid, until they eventually bump into their neighbors. Because they started with random orientations, they don't line up perfectly where they meet. The boundaries where these differently oriented grains meet are called grain boundaries.
Grain boundaries, so they're like defects or interruptions in the perfect pattern.
Exactly. They are regions of atomic mismatch, sort of like fault lines in the otherwise regular atomic arrangement within each grain. So a polycrystalline metal is like a mosaic of these small, randomly oriented single crystals, grains, separated by these boundaries.
And if a material is made up of many randomly oriented grains, how does that impact its overall properties compared to a single crystal?
Ah, this leads us to two important concepts, anisotropy and isotropy.
Anisotropy and isotropy, what do they mean?
Anisotropy means that a material's properties depend on the crystallographic direction in which you measure them. We saw this earlier. A single crystal of copper, for example, has a very different stiffness, elastic modulus. If you pull it along the 100 direction versus the 111 direction, it's much stiffer along 111
Why?
because the atomic spacing and the strength of the bonds are different along those different directions within the crystal structure. So single crystals are often anisotropic.
Okay, so anisotropy means direction matters. What's isotropy?
Isotropy means the properties are the same regardless of the direction of measurement. Some single crystals happen to be isotropic for certain properties. Tungsten is nearly isotropic for elastic modulus. But more importantly, even if the individual grains in a polycrystalline material are anisotropic.
Which they usually are.
Right. If those grains are numerous and randomly oriented, then the material as a whole often behaves isotropically. The directional differences average out over all the randomly oriented grains. So a typical lump of polycrystalline copper will seem to have the same stiffness no matter which way you pull it.
Ah, so the randomness averages out the anisotropy of the individual grains.
Precisely. However, sometimes during processing, the grains in polycrystalline material can develop a preferred orientation, a sort of alignment. We call this texture. And if you have texture, then even a polycrystalline material can exhibit anisotropic properties, which can actually be desirable in some applications, like optimizing magnetic properties in transformer cores.
This is fascinating,
Yeah.
but it brings up a really important practical question for me. How do we actually know what these crystal structures are? How do we measure the distance between planes or figure out if something is FCC or BCC? We can't just, zoom in with a microscope and see individual atoms lined up.
That is the crucial question. And the answer lies in a truly groundbreaking technique called X-ray diffraction, or XRD. It's the primary tool that has allowed us to determine essentially everything we know about crystal structures.
X-ray diffraction.
Mm.
How does that work? How can X-rays tell us about atomic arrangements?
It relies on a phenomenon called diffraction. Diffraction happens when a wave like light, or in this case X-rays, encounters a series of regularly spaced obstacles whose spacing is comparable to the wavelength of the wave.
And the atoms in a crystal are regularly spaced obstacles.
Exactly. The rows and planes of atoms in a crystal act like a diffraction grating for X-rays, which have wavelengths on the same order of magnitude as the distances between atoms.
Okay, so the X-rays hit the atoms, then what?
The X-rays are scattered by the electrons of the atoms. Now imagine X-rays scattering off parallel planes of atoms within the crystal. If the scattered waves from adjacent planes travel paths that differ by an integer multiple of the X-ray wavelength, they will be in phase when they emerge, meaning their crests line up with crests and troughs with troughs. When this happens, they reinforce each other, this is called constructive interference, and produce a strong, detectable diffracted beam at a specific angle.
And if they're not in phase?
If the path difference isn't an integer multiple of the wavelength, the scattered waves will be out of phase. Crests line up with troughs, and they will cancel each other out through destructive interference. So you won't detect a strong beam at that angle.
So you only get strong signals at very specific angles determined by the atomic spacing.
Precisely. The condition for constructive interference, for getting that strong diffracted beam, is described by a fundamental equation called Bragg's law.
Bragg's law, what does it say?
It's actually quite elegant. Nalin AGH Else Seti. Here, lambda is the wavelength of the X-rays being used, which we know. DHKL is the distance between parallel crystallographic planes with Miller indices, HKL. This is what we want to find. Le is the angle at which the incoming X-ray beam strikes these planes, and also the angle at which the diffracted beam leaves. And N is just an integer 1, 2, 3, representing the order of diffraction. Usually we'll look at N1.
So if we know the X-ray wavelength and we measure the angle where we get a strong diffracted beam, we can calculate the spacing d between the atomic planes that cause that diffraction.
Exactly. We can calculate DHKL for various sets of planes.
How is this done in practice?
We use an instrument called a diffractometer. Typically, you prepare your material as a fine powder or use a polycrystalline sample. This is important because the powder contains millions of tiny crystallites in random orientations, ensuring that some crystallites will always be oriented perfectly to satisfy Bragg's law for every possible set of crystal planes, like 100, 110, 111, etc.
So the randomness helps here.
It does. The diffractometer shines a monochromatic X-ray beam, meaning just one wavelength, onto the sample. The sample and a detector then rotate, and the detector measures the intensity of diffracted X-rays as a function of the angle, usually plotted against twice the Bragg angle.
And what does the output look like? What's the fingerprint?
The output is a graph, a diffraction pattern, showing peaks of high intensity at specific two angles against a low background intensity. Each peak corresponds to a specific set of crystallographic planes, HKL, that satisfied Bragg's law at that angle.
So a series of peaks at different angles.
Right. From the positions, the two values of these peaks, we can calculate the DHKL spacings for each peak. Then, by comparing the pattern of these spacings, and also which peaks are present or absent, because certain structures have rules about which HKL planes can diffract, like for BCC, H plus K plus L must be even, we can deduce the crystal structure, FCC, BHCC, HCP, etc., and calculate the precise size of its unit cell, the lattice parameter. It's truly like a unique fingerprint for the material's atomic structure.
That's amazing. So X-rays let us decode the hidden atomic architecture.
It's an incredibly powerful technique. It's how we've mapped out all the structures we've been discussing.
And just to wrap things up, let's briefly circle back one last time to those non-crystalline solids we mentioned right at the very beginning, the amorphous ones.
Right, good point. As we said, non-crystalline or amorphous solids completely lack that long-range repeating order found in crystalline materials. If you looked at amorphous silicon dioxide glass versus crystalline silicon dioxide quartz, the local bonding, how each silicon atom connects to its neighboring oxygen atoms, might be quite similar in both.
So the immediate neighborhood looks okay.
Yeah, the short-range order can be similar, but as you look further out in the amorphous material, that order breaks down completely. There's no repeating unit cell, no lattice. The atoms are in a disordered random-like arrangement, similar to a liquid structure that's been frozen in place.
And you mentioned this often happens with rapid cooling.
Yes, rapid cooling, quenching, from a liquid state is a common way to produce amorphous solids. If the atoms don't have enough time, enough thermal energy to move around and find their preferred low-energy crystalline positions before the material becomes rigid, they get locked into that disordered liquid-like structure. Glassmaking is a perfect example of managing cooling rates to avoid crystallization.
Wow. Okay, that was quite the journey into the incredibly structured and sometimes deliberately unstructured world beneath the surface of solid materials. We've really unpacked the fundamental difference between crystalline and non-crystalline structures.
We have. And we explored the intricate details of those key metallic unit cells, FCC, BCC, and HCP, figuring out how atoms pack inside them.
And learn that whole new language for how we address specific points, directions, and planes within them using those indices.
We also managed to connect these tiny microscopic arrangements to real-world macroscopic properties like density, transparency, and even ductility, how materials deform through slip on those dense planes.
Plus, we touched on polymorphism, allotropy materials, changing structure, and that crazy tin disease story.
And critically, we saw how X-ray diffraction acts like our eyes, allowing us to actually peer into this atomic architecture and decipher it using Bragg's law. It takes us from perfect single crystals used in electronics to the complex network of grains and grain boundaries in the everyday metals all around us. It really is all about order, or sometimes the strategic lack of it.
So what does this all mean for you listening? Well, next time you pick up an aluminum can, or maybe just look through a window, I hope you'll have a new appreciation for this unseen yet incredibly influential world of atoms. Understanding how they arrange themselves is just fundamental.
It really is. This foundational knowledge is absolutely essential for understanding why materials behave the way they do, and crucially, how we can engineer them for specific uses, whether that's making lighter, stronger alloys for cars, designing more efficient semiconductors for computers, or even predicting why an old tin artifact might crumble in the cold. It truly is the invisible story behind everything solid.
So next time you encounter any material, maybe pause and consider that silent, invisible dance of its atoms and the profound impact of their specific arrangement.
And perhaps it leaves you with a question to ponder. How many other hidden structures dictating the properties of the world around us are still waiting to be fully uncovered or better understood? And what new materials, what new possibilities will that deeper knowledge unlock for us in the future?
A truly thought-provoking question to end on. Thank you so much for joining us on this deep dive today. We hope you're feeling a little more well-informed and definitely a lot more curious about the materials that make up our world.
And on behalf of the whole Last Minute Lecture team, thank you for tuning in. Keep learning and keep questioning.